Hello everyone, it's been 12 hours. I slept, I ate, well rested, went to Walmart already. Alright, let's continue this. Where were we yesterday? So we did the subtree sum. So we got that part done. So the next one will be to do the DFS itself. Okay. And I am intending to return int, so I will be able to not using an external like global variable to keep track of how many splits we can make. So again, to recap, the ideal is we're just gonna go after we create this subtree sum, and we're just gonna go through them, and every link, every edge that we find that can't be split, we will split. Because yesterday we made some efforts to prove, or at least I think we have proved, that greedy works, right? If you find a split, then you should do it, because there's no benefit of not splitting it, right? Because if you don't split, eventually you will have to split, because we have this restriction that the input is generated such that the edges, no, not this one, the sum of values is divisible by k. But we have this, so if you are able to break it down into components whose sum is divisible by k, and you have an edge you decide not to split, and at the end you will have to split no matter what, because that will make it better, right? So now what we're gonna do is we have a node, right? So basically we're gonna call here, we could call it DFS, right? We'll call it with the root, and I just arbitrarily set 0 as the root, and the 0 doesn't have a parent. I'm going to do a graph, and I'm going to do values, and I'm going to do k. So it's exactly the same. Where is k? I didn't see k. Okay, we need to put k here. So we need to say k, right? So exactly the same, but after I should actually node. So this turns values into subtree sums, okay? And then we're at the root. What we do, we'll check it's all the children, right? We check all the children. The first one that allows us to split, we will split. So we'll say for int child of graph node, right? So another question I have is, no, I think as long as we check for parent, we should be fine. For each one, right, basically we have an edge from node to C. So we say if I split it, will it work, right? And then we say if subtree sum, that's fine. We can use subtree sum because we pass values to it. So if subtree sum C mod k is equal to 0 and subtree sum node, right? So subtree sum node is the total, right? This is because we say the node is actually the root, right? The subtree root. So we probably need to do something about that as well. So that is the root. You know what? I actually prefer to call it root instead of call it node. So I'll call it root. Okay, I'll call it root. So if the subtree sum root minus subtree sum child, if that mod k is also equal to 0, right? Then this is where we will split, right? We will split. How do we split? We just say, we'll split the two, right? And on one side, I can just call DFS C, right? And we also have to do, we can say if C is equal to parent, or we can continue. So we skip the parent. Right, so it will be C root graph subtree sum and k. Okay, that's that, and that's the how many split I can get from here. right? And we also need to say how many we can get from the other side, but the other side is a little bit tricky. So let me just do int split 1, okay, is equal to this. Now we're gonna get split 2. Split 2, we need to make some changes, right? We need to make some changes. So one of the change is we need to update its value because I just passed on that. I need to say subtree sum root minus equal to, oh, we actually, that's not right because, oh boy, plus k, all right. Oh boy. Yeah, because it's all mod, so I need to say this minus this plus k mod k. And then this is going to equal to the same thing, which is subtree sum root minus subtree sum c. Actually, we should probably do this one first because it might get updated, right? And then we do this mod k plus k mod k, right? So plus k mod k, that's the new root. And now we do this, and then we do the second split on that, right? The number of splits on that, and we basically plus them together, right? Plus them together. So I can say maybe return this plus DFS root parent graph subtree sum and k. Expect patronum. I think I'm missing something here. I think there's extra of this. Right, so you just put them two together, right, and you keep going. And eventually you'll hit something where you go both and they don't work. That's actually a good question. What if the left doesn't work? So you cannot split out the left, and then the right doesn't work. Would that be a case the left and right both doesn't work? It's possible, right? It's possible. So if they both don't work, so this is, I'm at the root. I say I cut my left. If it works, done, right? I just do that. I try the right. Any one of them. Right? Any one of them, it works. That's good, right? We all just do it. But we all also be possible that you go through every one of them and it does not work. Okay? It does not work. So when that is the case, that just means there's no splitting from the current side. So you need to go just one level lower, right? One level lower. So how would you go one level lower? You go through them again, right? You go through them again, and you just start from here, and then you keep going. Start from here, you keep going. And then, right, so basically I have the subtree, and then whatever they split. Because from this perspective, you have, let's say, 2. And then from this perspective, you might have, this tree can split into this amount. No matter how many, right? And they're all connected to 1, which means if this doesn't work, right, then you shall say no split on the current level. Find splits in children's level. Not specific component, right? Number of component. Then we go again, right? We say component plus equal to DFS C root graph subtree. We're trying to find how many is in each one of them. And then once we're done, we'll say return component minus graph root dot size. Right? If I have 3 children, and each one give me the total number of components. The first one has 2 components, second one has 2 components, and third one has, let's say, 3 components. And you add them together, 2 plus 2 plus 3, right? That will be 7 components. But the answer should be, because one of the components is always connected to the parent, right? So its total number should be 1, 2, 3, 4, and 5. It should be 5 components. That is not what I had in mind, because I would, hold on, let me try it again. So we'll have 1, we'll have 2 here, 2 here, and then 3 here, right? So that's 7. But 1, 1, 1 is gone. So plus 1. So basically you're minus this and then plus 1. So at the end, I think we will return this. All right, let's see. All right, let's see if this one's right. Oh, deadly signal. What is this? I have an error called deadly signal. Oh, because I struck Stack Overflow. Okay, we'll deal with this one later. What in the world? Okay, let's see. The regular case, would it work? Nope, we have deadly signal. Okay, let's just use one of the... Man, it was bad. That was bad. That was so bad. Okay, where? Yep. Okay, that's fine. Totally fine. We just need to figure out why. So we're starting from 0. You know what? Why don't we start from 1 so it's easier for me to debug? Alright, it's easier for me to debug. So yeah, I'll start from 1 and then see how it goes. Okay. And it's the DFS side, which means this one's fine. It's this one. Oh, I see why. Because I did not detach. Oh, Lord. Oh, how do I do set? Hey, I thought, where is Gemini? Okay, I just do set that way. Okay, I know why. Because once you've done that, you have to delete the thing, right? Delete the thing. So it's td set. Is that how you do it? Int set. And I think set doesn't have add. What's the API of set? Put, push, add. Wait, what? Insert? Is that the one? Alright, I need to see. Set.
No?
Yeah, I'm telling you, I can never really understand this. What the hell?
Summarize it.
Yeah, for sure I can do. Oh, see also insert element. I'm not sure if that's okay. Different way you can summarize. A set. Insert. Yes, it's insert. So we'll do insert here. Okay, insert. Yeah, the signatures are wrong, but that's fine. This will be set. Okay, and then this will be a set. All right. So now what we do is we do here, and then we're gonna delete it. Okay, we're gonna delete it. We'll do it. Graph. Madre mia. Dot. Delete. Remove. My God. What? Erase. I'm not even 100% sure. There we go. Erase. Yep. So we'll do erase C and graph C dot erase root. Okay. All right. This one we shouldn't hit that deadly signal. Let's see. Sorry. Do we have a go? Deadly signal again. What?
No.
All right. Can't do this anymore. Let's debug this. Yeah, we debug. That'll be fun. I really like debugging these days.
The first ingredient is corn. The second ingredient is corn gluten meal.
All right, this is a terrible brand. I got duped. I feel very unhappy. No wonder it's cheap. I thought, oh my goodness, I thought we were giving them a good break of a different flavor. Now I feel stupid.
Oh wait, meow mix is the same.
Meow mix is the same?
Yeah.
Okay, I feel a bit less stupid, but still not happy. Actually, I'm not sure. Is this the way to initialize it?
Don't get fooled, Jeff. No, you won't.
Oh yeah, I think that is the way to initialize it. What's the third one? Values. Dude, I have one more. Okay. Alright, stupid. Let's do this. Max.
No.
Where do I put? I'll put it inside. How about we do that? We put it inside. We put this one inside, and then we will see line build it. This is number 21. Oh, shoot. Why didn't you tell me? Oh, it does tell me. N edges values. Okay.
No, I want to go on a cruise.
You don't want to go to cruise? All right. Oh, let's see what we have. The first thing I want to see is the subtree stuff. So I have 0, 0. Actually, I'm not sure even it's right. I don't want to connect it, but I think I have to connect it. And you know what my tree looked like. Alright, I thought it's gonna be a 10-minute effort. I think this one's gonna take a while. Alright, let's bring
You can do it.
the gun.
The big gun.
The big guns. Okay, so I need to put 0 first. So let me just delete this. Okay, so I have 0 and 2, right? And 2 connects to 4 and 1, and 1 connects to 3, right? And 0 is 1, 2 is 1, 0, 1, 2, 3, 4 is 4, 1 is 8, 0, 1, 2, 3 is 4. So the sum 4, so we all say this is 8, this is 12, right? And this is 4, this is going to be 17, and this is 18. Alright, so we shall see. Oh, this is very wrong. This is as wrong as it can get.
Very wrong.
Very, very wrong. Okay, what did I do? Oh, I put in, I see what I put in. You're correct. We put in the remainder. That's what we put in, okay? So 0, remainder is 0, that is correct. So okay, so remainder wise, this should be 0, because we're divided by 3, right? We divide by 6. This should be 5, right? Because 12, yeah, this is 5. And this is 4, this is 4, this should be 0 as well. Okay, let's double check. So we should be looking at 0, 0, 5, 4, 4. 0, 0, 5, 4, 4. That is correct. Okay, that is correct. And where are we? We are coming in. So C is 1. Wait, how come C is already 2?
I don't know.
So I'm going from 0. Oh, so it is 2. Huh? Hold on. Let me redo this.
No.
Let me redo this. Alright, C is 1. 1 is not equal to. So, wait, hold on. C is equal to 1. What in the world? I start from 0. C should not be 1. Nah, C is 2. And 2 is not divisible. Coming back. Done. C is 2. Then we do DFS from 2. So root is 2. Okay, parent is 0. So from 2, the first, that's actually not true. That is true. C is 1. Okay. Not equal to. Oh, C is 0. Oh, wait, hold on. That's the first one. Okay, continue. Next, C is 1. Not equal to. Okay, C is 1. So this is good. because if I split, this is good. I think 1, 3, yeah, that's the way, right? It's good. And this minus, it's 5. I see the problem. I see the problem. I see the problem. Because you should not supposed to use this. You should just pass it down. Okay. I should pass this value down as well, because this is acting as a root. Let me think. Let me think. Yeah, I think the value should be passed down, because you are representing this entire thing. Okay, so I think the value should be passed down. So the value should be passed down, which means subtree sum. Which means subtree sum. C shall equal to subtree sum root. Okay. Let's give it a shot. You were shocked. That is. Alright, that's fine. Let's rebuild it and try it again, man. Do 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 So this one's good, and root is 2 minus this, so that's also good, right? Yes, c equal to 1. So both are good. So the root is 2, because I'm going to split this, right? And I'm going to say this one minus this. Yeah, this minus this. That's actually still 0. Or erase. And then we're going to say DFSC, which is this part, right? This part. And okay, so the root is 1, okay? Parent is 2, the root is 1. Then C is 3. Not equal. We try it, but this is bad. So next, we get out. Yep. Right. So root is 1. We get out. And we go to the next one. Yeah, don't worry, I'll deal with this. Okay, so I'm at 1 and I'm looking down at 3, right? We're looking down on this one. And I think this is where we break down, because what we say is I will just check this, right? Check this. And now I go to here, right? Basically we say subtree sum. Yeah, we can actually keep going, right? We keep going. So C will be 3. And then I'll update it. This becomes 0. So com plus equal to, so we're gonna do, yep, root is 3. Then go down. 3 doesn't have any. Oh, it has 1, but it will continue. Boom, come down here. Comp is 0. Right. And it doesn't. Oh, I see. I see. Okay. I forgot to check the parent. If C is not equal to parent, okay. I'll try one more time. Let's try this one more time. That is brutal. Oh, I see why. Because, oh my god. Oof. So this, okay. I see. So maybe what I can do is this is -1, right? If this plus -1, -1, so I get 1, 2, 3, 4, right? And I add myself. So basically will be component, something like this. All right. Man, we just keep trying different ways. One of them will work. All right, try it again. Yay! I just got one of them to work. So I have actually another test case, the ultimate test case where everybody is 0. All right, so 1, 2, 3, 4, 5. All right, if all 3 pass, okay, I think we can write something down. This might be the solution, might be. Took a long time. 2872. Use greedy. Right, whenever, no, okay, one step at a time. First, choose any node as the root. Perform DFS to find the subtree sum. Then DFS again for each node. If cutting, right, any of its edges results in 2 components where the sum of both are divisible by k, we will honor this cut. It can be proven that this greedy approach works. Because if we choose not to cut, right, and resolve and claim that the result is gives us the most number of components, we can always, right? We can always make the cut, make that cut again, right? We can always make that cut again to obtain even more components. Hence, cutting an edge, that's cutting any edge that satisfies the requirement is a good strategy.
No.
Yeah. So with this, it's actually going to be ON solution, I think. Okay. Moment of truth.
No.
And I also think I handled the edge cases, right? Because the sum, I actually just do the modulo and then, yeah, let's try it. Let's see what we got. Come on. Oh, yes. Oh, yes. Satisfying. Although it took 1 hour and a half. And I'm pretty sure if I kept doing it yesterday, I probably wouldn't be able to. Because first, I'm going to get very frustrated because things just don't work. Right? I'll get frustrated. However, the main idea was acquired yesterday. So that was good. All right, let's check the solution. DFS. We're given an undirected blah 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 Vatican blah blah blah. Can we get a single component? Once we pick a node as a root, we can break the tree down into smaller parts, called subtrees, based on the parent-child relationship. The tree is undirected, so we can choose any node to be the root without affecting the result. Now let's think about how we can use recursion to solve it. We want to calculate the sum of each subtree. Agreed? After calculating the sum, we need to check, is this sum divisible by k? If it is, we can detach the subtree at that point because it forms a valid component. But what if the sum isn't divisible by k? In that case, we need to carry over the remainder, the leftover part, when divided by k, to the parent node. This way, the parent node can combine its remainder with its children's remainders to check if the total sum becomes divisible by k. This recursive process naturally fits. Start from the leaf of the tree and compute their sums. Propagate the results up to the parent, adding up the remainders modulo k. Whenever a subtree sum is divisible by k, count it as a valid component. So I will presume that this will actually do a one pass, something like that. Okay, let's see. This is just to create an adjacency list. I need to get it larger. What in the world is this? What is this? Vector of int. Oh, wait a second, you don't have to delete it at the end? Because it's not dynamic. It's basically a list of vector. Okay. Okay. Start DFS. Are you gonna hear me say this a lot? Because just all these tricks and stuff in C++, like I completely forgot about this passing reference. I was thinking, you need to create a global variable. You don't, because it can pass by reference. Okay, sum of the current subtree, and then you go blah blah blah. You get a sum. Yes, and then add the value of the current node. Sum plus equal to this. Yes. Oh, that's it? Bloody hell, that's it. Yes, sum is the subtree. Basically, you say whenever you find a subtree that is divisible, you split out, which is true, right? Which is true. And you will just split out, and then you return and just keep going. As you build up the subtrees, yeah, it doesn't matter. Yeah, exactly. This is exactly what we're talking about, right? Exactly what we're talking about. It's just any subtree that's divisible. I didn't. Okay. Yep. That's good. I'm not going to read the BFS. Don't think it's a good use case for BFS. Probably make things more complicated. Topological sort. Onion sort. Onion sort. Okay, we have in degrees. Dependencies can be represented by the number of connections each node has. For instance, a leaf node has exactly one connection. And as we process it, it's so you basically you pick the one with 1 degree and then you just build in. Oh yeah, I guess you can do that. Right? And then you get in degrees and you have a queue. Right, if it's in degrees of 1, you push it in, and then the queue comes out. Check if the current node's value is divisible. If it is, you pop it out. The current node's value is divisible. Propagate the value to the neighbor nodes. Yeah. So the neighbor node is just absorbing its children's values. And then each one's divisible. If it's not, what does this add value do? Because I'm looking at this node, right? Oh, this is the value to be add. I know. So everyone will add this value. Yep. Okay, I see how this one goes. I'm gonna write another solution because I do like this idea. I'm not going to do the BFS. I think DFS is more intuitive for me. All we need to do is let's create a new one. But overall, it was successful, right? It took a while, but it was successful. I might not be able to compete with AI, but at least won't be butchered.
Yeah.
Yeah, this is the DFS solution, right? From the official solution. It uses the same idea as solution 1, but but its implementation, right, is much simpler because we can decide on the compute component as we calculate the subtree sum, right? We still need the greedy, right? But we can count a component the moment a subtree sum becomes divisible by k, right? The moment it becomes divisible by k, right? In other words, we don't need a second pass. Okie dokie. First things first, we need to redo this. Oh, and we have a new graph. Also, we can use a trick to make the graph easier, faster. Graph representation. Right, so what they do is std vector, right? Wait, what do they do? Graph. Is that how they do? Yep. Variable length array in C++ are a clang extension. I don't know what that means. I don't know what that means. It's not compilable? No, it's fine. And then essentially the same. Oh, by the way, this morning as I was going to Walmart, there are Chinese like ads, you know, those like you know, those things the politician used to use, has a little cardboard they stuck on the side of the road, and there's a Chinese sign there that says roasted full lamb in-house. So basically you call them, they come to your house and roast a lamb for you. Exactly, that's why I was like, oh my god, that sounds terrible. Alright, so this is our graph, and then I think I will simply just do this and we'll have the solution, right? I just return DFS this graph values and k, and now I just need to do this DFS private yeah, let's call it node or root parent std vector int, I don't know, I just don't know what's the signature. Oh, that's the signature. Interesting. Do I need to say? I don't. Huh. I guess it's directly passing the address. Man, C++ is complex. All right. Anyway, what we want to do. Oh shoot! I forgot one more thing. Hold on. Call this. And we'll pass a reference result. Okay, res sum, yes, 0 for child of graph root. C sum if child is not equal to parent. DFS child parent graph values k rs sum equal to sum plus c sum mod k if sum values root. If sum mod k is equal to 0, res plus equal 1, return sum. That's it. As simple as it gets. Oh wow, this is simpler. Look at that. Look at that. Good. Good man. Alright, that'll be it. 2 hours basically, because I spent 52 minutes on this one. But it's good. Good result. Alright, that'll be it. See you guys tonight.